Greetings and welcome to the baking soda stoichiometry lab. Baking soda is commonly used for household cooking and cleaning. Baking soda is commonly used for household cleaning and cooking. It's often used for producing cakes, cookies, and other items, usually for its CO2 production. Once baking soda decomposes, it produces large quantities of CO2. When baking soda is heated to about 50 degrees Celsius, it produces carbon dioxide. You've probably seen the effects of baking soda being heated. If you've ever heated up pancakes or used pancake mix, baking soda has already been added. In the left picture, you can see the effect of baking soda producing CO2 on a skillet. If you've ever used a bread mix or a cake mix, baking soda has been added to those mixes, and you can see the spongy effect of the cake or any other bread mix because of baking soda. The CO2 bubbles form air pockets inside of those cake mixes. The purpose of this lab is to identify the decomposition reaction of baking soda when heated using the process of stoichiometry. Decomposition just means the breakdown of baking soda. Again, when you heat baking soda, it breaks up into other chemicals, some of which are released into the atmosphere, but some other chemicals stay inside of the dish and they're left over. These chemicals are not harmful to humans, but we still need to identify them and see how much is left. Stoichiometry is just a big word that chemists use that basically means a ratio or a proportion of measurement. So stoichiometry is very similar to you making you following a recipe. If you've ever followed a recipe, you're basically following stoichiometry as long as you're following the recipe the way it's written down. Chemists use stoichiometry to make sure they're following the recipe of chemistry, much like a chef would follow a recipe inside of a restaurant. So in this lab, students were given 3 possible chemical equations for the decomposition of baking soda, and they had to balance each equation for use using stoichiometry and calculate the remaining powder, whatever it may be, after we burned it. So the first powder that we were given was baking soda, and then it was broken down into NaOH, which you may know is Drano, or floor cleaner, sodium hydroxide. So what we saw, so this is the first potential chemical equation that may occur with baking soda. So we're not sure if this is actually the chemical equation that may occur, but students were supposed to figure out if this was the chemical equation that the decomposition equation that occurred. So what students did is they balanced the equation, and we ended up finding that it was already balanced with a 1:1:1 mole ratio, and that was using stoichiometry. And then what students did is they used their stoichiometry and they calculated from 2 grams of baking soda, which is the NaHCO3, and they converted that using dimensional analysis, and then they used a mole-to-mole ratio, and it's color-coded on the chart where you can see the mole-to-mole ratio with blue and red, and they converted it to moles of NaOH. Now this is moles of NaOH as if the sample of baking soda had been heated to 50 degrees and let sit on a burner for a sufficient period of time. And what they found was that 2 grams of baking soda should produce 0.95 grams of NaOH. Now you'll notice that there's a coloration key at the very bottom of the screen. The green means remaining, and the blue means evaporated. Now the CO2 in this sample should have evaporated from our sample, so we should have lost mass, and the CO2 in our sample should have floated away, and the remaining amount should have stayed there. So we went from 2 grams to 0.95 grams. So if we reweigh our sample, it should have lost mass and gone from 2 grams to 0.95 grams. So if we heat our sample and it goes from 2 grams to 0.95 grams, we know that this is the chemical equation And this indicates that this is the chemical equation that is the breakdown of baking soda, basically. So let's see what other chemical equations we have as possible candidates for the breakdown of baking soda. The next one is baking soda breaking down to sodium oxide. And so we have another balanced chemical equation, and this one breaks down to sodium oxide and then CO2 plus water. So in this one we get water vapor. So we have water vapor, which is different, that's unique. The kids were also looking for water vapor in this chemical equation. If they ended up seeing water vapor, they knew that this could be a potential equation. Notice that the water vapor and the carbon dioxide would both evaporate under heat. So they would both evaporate, and the only remaining substance that would be left would be the sodium oxide. Again, students calculated that 2 grams of baking soda would give you a certain amount of remaining substance. However, the amount was different and the substance was different. And in this case, they calculated that you would get 0.738 grams of sodium oxide from baking soda, sodium bicarbonate. So this is a contrast, and this is kind of how this lab works. In the previous one, or the previous calculation, we discovered that you could get 0.95 grams of sodium hydroxide, and therefore you would know that sodium hydroxide was present just by the weight. But if there's sodium oxide present, you would know that you could identify that it was 0.738 grams. So just by the weight, you could identify which chemical equation was actually occurring just by heating up baking soda. So just by weighing it using stoichiometric skills, the students would be able to identify what substance was present. And all of that is based around the principle of stoichiometry. Next, we have one more equation, one more chemical formula, and students identified that this one we would get one more substance, and they identified that this one would give us 1.26 grams of this substance. And again, this substance would also have carbon dioxide. So all 3 substances have carbon dioxide, which is where the bubbles came from in your cake or your pancake or anything like that. But this other third one would have water. So reactions 2 and 3 both have water. All 3 of them have carbon dioxide, and all 3 of them have different weights. So students were here to identify, students were trying to identify which one of these 3 reactions was the true decomposition reaction of baking soda, and all they had to do was heat this up and record the mass of each one of these of 2 grams of heated baking soda, and it would convert to a new substance. So if it was the first reaction, it would be 0.95 grams or something close. If it was the second one, it would be 0.738 grams or something similar. And if it was the third one, or the third reaction, it would be 1.26 grams or something similar. Alright, so let's go ahead and go to the procedures. instantly, what do you see? Everyone come take a look.
Condensation.
You see condensation. Is that water vapor?
Water?
Yeah, that's what you said.
So we have water vapor. What does that tell you? There's two reactions that have water. So does that eliminate one of the reactions?
Yes.
Yes, that eliminates one of the reactions, does it not? All right, so let's go ahead and start going. Let's start cooking with the other ones. Switch off. Y'all can start cooking. As you can see from the data table, we have 5 trials. This represents several different classes, and all of these different classes got somewhere close between 0.6 and 0.8. All of this averages to 0.72, which is very close to our second equation. Now also note that our classes encountered water vapor, which is very similar to our second equation. So it would seem that our second equation seems to fit the bill for what we're dealing with. Finally, we need to do one more calculation, and this is called the percent yield calculation. Now, the percent yield calculation deals with the actual yield over the theoretical yield. Now, we hypothesized that we would get, for calculation number 2, 0.738 grams of sodium oxide. Now, it turns out that we only got 0.72 as our average. So what we do is we put the actual, and so I took the average of all 5 trials, and we put that over our predicted. And so when we do that and we put that into our formula, we get a 97.56% yield, which is pretty good, but we're not ever going to get a 100% yield. Thank you. Have a nice day.